right, this is APAB Calculus, and we're doing the Intro to BC unit. This is topic number 2, integration by partial fractions. So, a quick heads up, I'm not going to do the steps for how to do partial fraction decomposition, which is a pre-calculus or algebra 2 topic, in this video. They're listed in your packet that you're working through, but also, if you want to look into that, I will have those videos included from my pre-calc class in this playlist as well, even though they're not strictly an AP topic, to give you a refresher on how partial fractions work. But I'm not going to go all the way through that again because those videos already exist, so I'm going to post those pre-calc videos for you to watch. Don't panic if you don't remember how to do it. That's totally why the videos are there, and it's okay to review the stuff, but I just don't want to make the same video twice. So we're going to go in and jump into this like we know how to set up this decomposition. So here's the situation. Sometimes I have an example where this problem could actually work with u sub, okay? So what I want to just show you really quickly is the difference between this thing, right, that I have as example 1, versus something that looks like this, 2x minus 3 on top of this x squared minus 3x minus 4. So, just to be clear, if you were handed this problem in AP/AB Calc, you would probably try and make this entire denominator u, and you'd be looking for the top to be a multiple of the derivative of that denominator, right? So, if your entire denominator were this u, this x squared minus 3x minus 4, the derivative of that denominator is a 2x minus 3 dx. So this thing right here, right, this version in red that is not the problem I gave you, this would absolutely integrate with u sub, right? This thing would be the integral of du over u, and you'd get that this is the natural log of the absolute value of x squared minus 3x minus 4 all plus c. So that's the way you'd see this as an AB topic, is that you might have a denominator that factors, but it doesn't matter because the numerator conveniently works with u sub, right? But that's not what's happening here, right? That's great, but that's not what's happening here, because if you look at our example 1, that numerator is not any multiple of the derivative of the denominator. That's not going to happen. So, this is a hint that we want to use partial fractions decomposition. So in a second, I'm going to erase all that red stuff that I did over there because I just wanted to show you the different kind of question you might see, right, where something works without this decomposition. So if I were going to do this decomposition, I need to take this x minus 9 on top of, and I'm going to factor that denominator fully, and I'm going to get an x minus 4 times an x plus 1. And you can double check that that works. You should always FOIL your factors in your head just to double check that you're right, because we all factor wrong sometimes. But in calc, it can have pretty drastic consequences, because after you factor, you still have a whole lot of problem to do, right? We still have a whole lot of stuff to do in pre-calc, and then we do the calc at the end. So if you factor wrong, it doesn't go well. So I get my partial fraction set up, right? I then need to get a common denominator on my right-hand side that is identical to the denominator that was originally on the left-hand side. That's the key here. They have to be the same denominator. So I notice that the denominator on the left-hand side has an x minus 4 and an x plus 1. That means the a fraction is missing an x plus 1 over an x plus 1. And the b fraction has only the x plus 1, so he's missing the x minus 4 over the x minus 4. Because the denominators are all exactly the same, and that's the reason this works, I can basically say that the numerator, x minus 9, equals the other numerator, which is all of this stuff. The other way to think about that logically is it's like you're taking this entire giant equation and multiplying by the quantity x minus 4 times x plus 1, and all the denominators cancel. I don't care how you get there, but what matters is that we get that the numerators only are x minus 9 equals an a times the x plus 1 plus a b times the x minus 4. Right? Now, there's a bunch of different ways to do this. The easiest way, in my opinion, is to do what I call clever substitution. This equation has to be true for every x ever. So if I conveniently pick x's that are useful to me, like easy x's that knock out one of these constants that I want to know, I can solve for the other one really easily. So I'm going to pick x equals negative 1. I picked that because that's the x that would make this first parenthesis go away. And I'm going to get negative 10, because that's what negative 1 minus 9 would be, equals 0 plus a b times a negative 5. So that means that b must be 2, right? And then I'm going to get x equals 4 as my other clever substitution, right? Because I want to get rid of that b. And I'm going to get negative 5 equals a times 5. Therefore, I can plus a bunch of 0, right? Because the b stuff would cancel out. So I can conclude that a must be a negative 1. So what that does for me, if we come back up to the top now, because all of that was pre-calc, is I can split this into two integrals. A over x minus 4, well, that's negative 1 over x minus 4 dx, plus the integral of 4 over x plus 1 dx, right? And So, oh, sorry, it's not a 4, it's a 2. My bad. I don't know where I got a 4. It says 2 right there. Anyway, sorry, computer froze for a sec. So it says 2 there. I don't know where I got a 4. So now I'm going to integrate these, right? So when I integrate each one of these, technically they are u sub, right? Your u is the x minus 4, but conveniently, if your u is an x minus 4, your d is just dx anyway. So this guy is going to integrate to the negative 1 times the natural log of an x minus 4 in absolute value, plus a 2 times the natural log of the absolute value of x plus 1 plus c. And that answer's not wrong. Sometimes you'll see it as other versions of that answer. The other way that you could see this answer if the AP wanted to manipulate some powers is they could see you put these powers up top and turn these into a natural log of, in the absolute value, an x plus 1 quantity squared over an x minus 4, because that would be the negative 1, which is also possible, right? Either of those box answers are likely. So what I want to point out is that when you're doing an integration by partial fractions problem, it's very rarely the integration that's difficult. It's mostly that you have to remember how to do the partial fractions decomposition, which is a pre-calc skill. As we move forward, we'll start to have some quadratic factors, and those integrations can be slightly harder because sometimes when you're integrating those quadratic factors, you're going to end up with arc trig, which I know none of us love. But as you get better at it, it's not so bad.